You've seen this 1,000 times without a second thought. A little padlock icon sitting next to a website address, or the word SSH typed into a terminal to log into a remote server. Every single one of those moments is a lock actually doing its job right now, and by the end of this, you'll know exactly what's inside it. That lock has a name, RSA, for Rivest, Shamir, and Adelman, the three researchers who published it back in 1977. And it's built from exactly two ideas we've already covered. Primes, numbers so hard to factor apart they're basically a wall nobody can climb, and that clock trick, modular math, easy to run forward, brutal to run backward. Watch them combine into an actual lock. Here's the actual situation. You're about to send something private, a password, a card number, across the open internet, where anyone could be listening in. The question this whole series has been building toward: how do you send a secret across a line everyone can see? Before any of this, the server already did something in private, picked two prime numbers, the exact atoms of numbers idea from our primes episode, and multiplied them. We'll use tiny ones so you can see it. 3 and 11. That gives n, 33. Now compute one more number from those same primes, subtract one from each, multiply those together. 20. This number, called phi of n, is the real secret. It only exists if you actually know the original primes, which is exactly why factoring n back apart matters so much. The server splits this into two keys. The public one, E and N, gets broadcast to absolutely anyone, including your browser right now. The private one, D, never leaves the server. It goes in a vault. Your browser takes your password, turns it into a number, and runs the exact clock trick from last episode. Raise it to the power E, wrapping around mod and the whole way. Watch it cycle through the wrap, just like the clock did before. That encrypted number, 16, not your real password, travels across the open internet. Anyone watching, including that eavesdropper from earlier, sees it in transit. But 16 means nothing without the private key, which never left the server. The server receives 16, applies its private key, 3, and runs the wrap in reverse. Watch it cycle back, and there's your original password, fully recovered. Only the server, holding that private key, could ever do that step. The only way to fake that private key is to factor n back into its two primes, exactly the wall from our primes episode. With our toy n of 33, that's trivial, 3 times 11. Multiply real RSA's primes together, though, and that wall becomes uncrossable. Real RSA keys use primes hundreds of digits long, and itself often runs past 600 digits. Factoring a number that size back into its two primes would take every computer on Earth far longer than the universe has existed. If any piece of that moved fast, that's the point of this being a series. Our primes episode is the full story on why factoring is so hard, and our modular math episode is the full story on that wraparound trick. This episode was just the two of them, meeting. So the next time you see that padlock in your browser's address bar, or type SSH to log into a server, you'll know the whole story. Two primes, a clock that wraps forever, and RSA, a lock that only the right key can ever open.